So what we want to talk about here today in our lecture is the principle of virtual work. You've probably heard this in various forms. If you're like me, it sort of goes in one ear and out the other. I want to work through it this time in a little bit of a different way than I would do it if I was teaching, like, for example, a finite element analysis class. So in a finite element analysis class, what I would do is I would start with the equations of equilibrium, and I would develop the principle of virtual work from those equations. In this case, I'm going to begin by introducing the idea of a virtual displacement and then demonstrate that it's equivalent to the equations of equilibrium. So what is the principle of virtual work? Well, it's an integral statement of the differential equations that govern equilibrium. So sometimes I think that gets lost in the discussion. So let's begin. What we want to do is we want to consider some body B in static equilibrium under the action of body forces, and we'll call those body forces B sub I, and surface tractions. And we'll call those surface tractions Ti, and we'll put an N in parentheses above it to remind you that those are tractions that are on a surface with normal defined by the unit vector N. Okay? So that, if we draw our conventional continuum potato, right? And so it's kind of just showing you it's a 3D structure. Okay? And then at this location, let's say that might be our unit normal vector N. And at that location, maybe we have a traction vector Ti that looks something like this. Okay? We're going to let S denote the boundary of this body B. Okay, and so that S is some combination of a surface that either has a traction or a displacement boundary condition. So we would say, and S is equal to the union of S sub T, which is our traction surface, right? Union with S sub U, which would be our displacement surface. Okay, so I'll define those for you and say where, number one, S sub T is a surface with specified tractions. Okay, and don't forget, a specified traction could be a zero traction, right? It could be a free surface too. That would be a traction surface. And then number two would be SU is a surface with specified displacements. Right, and remember, you can specify one or the other, but not both at any given point on the surface. Okay, so let's recall the governing equation of equilibrium. Okay, so remember that's just sigma ij, comma j, right, where the comma indicates a partial derivative with respect to xj, plus bi equals 0. We'll call that equation 1. Now I'm going to introduce a couple definitions, one for a stress field and one for a displacement field. So the first one I'm going to talk about is a stress field. So let me give you the definition of a statically admissible stress field. Okay, a statically admissible stress field is one that satisfies the equilibrium equations over the interior of B, and it satisfies also all stress boundary conditions on the surface with specified tractions S of T. Okay, now I want to define what's called a kinematically admissible displacement field. So let's do that. Okay, a kinematically admissible displacement field is one that has continuous derivatives in the interior of B. Okay, and those continuous derivatives are whatever order they need to be to satisfy those equations of equilibrium. Okay, and it also needs to satisfy the homogeneous form of the displacement boundary conditions on the displacement boundary conditions surface on S of U. Okay, so that all sounds sort of cryptic. Hopefully you'll see how it plays out. Basically, I'm going to have all the derivatives that I want, and if I have a stress, whatever that stress is, it satisfies equilibrium. That's really all they're saying. Okay, so what does the principle of virtual work state? Okay, let's write that down now. Okay, the principle of virtual work states that a continuous body is in equilibrium if and only if the virtual work done by all the forces, and those forces are internal and external. So a continuous body is in equilibrium if and only if the virtual work done by all forces is zero in a virtual displacement. Okay? Okay, so if we have to write that, we say that the virtual work, we'll call it delta W, which will be the sum of the internal work, delta Wi, right, plus the external work, delta We, right, and these work terms are the virtual work of internal forces and external forces. What we're saying is that the virtual work done must equal 0. Okay, we're going to call that equation 2. Okay, so we're going to focus, at least in this class, on mechanical problems. So I'll just note, for mechanical problems, the virtual internal work is the same as the virtual strain energy. Okay, so that would mean that I could write delta Wi is going to be equal to delta U, right? That's the virtual strain energy now. And that's going to be equal to the integral over the body B of going to be sigma ij delta epsilon ij, right? Where delta epsilon ij is going to be the virtual strain caused by the virtual displacements, dV. Okay, we'll call that equation 3. Okay, the external work on the system is the work that's going to be done from the body forces and the tractions. So the external work on the system is going to be given as follows. Okay, it's going to be given by delta We, that's the virtual strain energy from from some virtual displacement. There's going to be a negative sign here. That's negative because this is external work performed on the body. Okay, and if we think about what those terms are going to entail, there'll be a contribution from the body forces. That'll be the integral over the body B of the body force Bi times delta Ui, the virtual displacement, integrated over the volume, plus the integral over the surface Ti n delta Ui ds. Right? So there we have it. Call this equation 4. We're going to substitute 3 and 4 into equation 2. Right? And then we're able to write delta W, the virtual work, is going to be equal to 0. And it's going to be equal to integral over B sigma ij delta epsilon ij dV, then minus this term here, integral over the body Bi delta Ui dV plus integral over the surface of Ti in delta Ui ds. Okay? Call that equation 5. Now, hopefully you kind of are anticipating where we're going next. We'd like to put this all under a volume integral so we can combine all these integral terms. So the first thing we're going to need to do to make that happen is we're going to just give you the strategy. We're going to use the Cauchy stress formula in that surface integral to write the traction as the stress dotted with the unit normal. Okay, and then we're going to be able to invoke the divergence theorem. We may write the following. Okay, so remember this. I'm not going to derive it because hopefully you remember it if you're watching this video or taking this class. It's going to be equal to sigma ij nj. Okay, so we're going to use that Cauchy stress formula in equation 5, and then we're going to invoke the divergence theorem to write the following. Okay, so the total substitution into equation 5 looks as follows. Looks like delta W is equal to 0. Now everything is going to be under the same integral when we do the two things I said above. So we'll integrate over the body B of now sigma ij delta epsilon ij, right, minus bi delta ui, minus partial with respect to xj of sigma ij delta ui. Okay, so that will be integrated over the volume, dv. Okay, we'll call that equation 6. Okay, now what we're going to do is we're going to use the definition of strain in terms of displacements, virtual displacements. Okay, and we'll go ahead and carry out the differentiation that requires. Okay, so remember we have epsilon ij, right? If this would be equal to 1/2 times ui comma j minus uj comma I, right? We're going to use that, except these will all be virtual terms in equation 6. Sorry, that should be a plus. Okay, when we do that, we end up with delta W equals 0, integral over the body of the quantity sigma ij times, we'll put the 1/2 there, I guess. Remember, these are virtual displacements, so it'll be delta ui comma j plus delta uj comma I. Okay, and then we'll have that minus bi delta ui minus, and then we can carry out that differentiation. That looks like sigma ij comma j times delta ui minus sigma ij delta ui comma j. Right? So I think that's good. Let's integrate that over the volume. Call that equation 7. Okay, I'm just going to now group like terms. So grouping terms. Okay, I end up with delta W equals 0 equals integral over the body. Okay, I have a 1/2 delta uij and a delta uji multiplied times sigma ij, and over here I have a minus sigma ij delta I comma j, right? So what that's going to give me is 1/2 sigma ij. Now it's going to be delta uj comma I minus delta ui comma j, right? And what I'm going to do here is I'm going to take these two terms that have a delta ui on them. I'm going to write them as, so we have minus now, bi plus sigma ij comma j times delta ui, right? dv, we'll call that equation 8. Now I want to observe some things in equation 8. That term, so let me write this down. This term, delta uj comma I minus delta ui comma j, right? That gives us a skew symmetric tensor, right? So let's observe that. Okay, and if we multiply a skew symmetric tensor times a symmetric tensor in sigma ij, we get identically 0. So equation 8 reduces to delta W equals 0, which equals the integral over the body I can drop the negative because I can just multiply through by a -1. And now I'm left with sigma I j, comma j, plus bi delta ui dv, right? Call that equation 9. So what can we say? Well, we never defined what this arbitrary virtual displacement was, right? So because delta ui is an arbitrary virtual displacement, okay, we can invoke the fundamental lemma of variational calculus to get the following. That sigma ij, comma j, plus bi is equal to 0. Let's call that equation 10. So what does this mean? That means that the Euler-Lagrange equations that result from the principle of virtual work are precisely the equilibrium equations. Okay? So, again, one thing we didn't do, we didn't explicitly extremize anything, right? We just invoked the fundamental lemma of variational calculus. So we're not saying that something is a minimum at this stage, at least. But what I do want to show is that the principle of virtual work is simply an integral statement of the equations of equilibrium. Okay? They are equivalent. Okay? Let me make a few remarks now about this principle, and then in the next lecture we'll do an example. Number 1. Okay, the principle that we just derived is independent of any constitutive law, right? We never said how stress and strain were related, right? Also observe that in equation 8, the body forces, the surface tractions, and the stresses are all constant, right? Those are not changing throughout the problem, right? The only arbitrary quantity is the virtual displacement term. And kind of a corollary to that, the stresses that we had were independent of the virtual deformations. So what does that mean? It means that there's no relation between the statically admissible stress field and the kinematically admissible virtual displacement field. Furthermore, the stresses don't need to be the actual stresses, just statically admissible. And also, the displacements don't need to be the actual displacements, just kinematically admissible. And the last comment I want to make is that this principle is not, at this stage at least, is not an energy minimization principle. Okay? Or an energy conservation principle. This principle is valid even when energy is not conserved. Right, so for example, maybe something like plasticity, right? It would be valid still then, even though energy is not conserved during plasticity. So I guess one thing that's worth noting is I think sometimes you spend so much time in discussing these definitions, it's not obvious what's the point. A couple things are worth noting here. One is that we're going to show in subsequent lectures that at least for elastic materials, and we're going to focus on linear elastic materials, this principle does turn into an energy minimization principle. In particular, we're going to get the principle of minimum total potential energy out of this. So it does turn into that, but we have to specify the constitutive law for that to hold. In particular, the strain energy has to be the strain energy density rather has to be a potential function, which is true only for elastic materials. The other thing that's worth noting is that oftentimes you need these equations that, for example, equilibrium, in an integral form. Why? Because it's much easier to develop approximate solutions for these problems if they're in integral form. And so if you took like an advanced FEA class from me, we showed how to do that particularly. But those are two reasons that these equations, the principle of virtual work is valuable, is that it admits an integral equation form so that we can develop approximations if that's the direction that we choose to go. It also will lead to an energy minimization principle when we select an elastic material. So we'll talk about that in upcoming lectures.